Alright, so picking up where we left off, we had our next example, which is example number 5, which is a triangle is inscribed in a semicircle of radius 5 as shown below. Find the triangle with the largest area. So we label our triangle here. So we know that the radius is going to be 5. And then if we put the origin here, then we can call this x and we call this y. So then our objective function is going to be the area of that triangle. So we have our Q, and the area formula for a triangle is 1/2 its base times its height. So in this case, it's going to be 1/2 x times y. Then we need our constraint. Well, the fact that our triangle is constrained inside of a semicircle with radius 5 means that if this is at the center 0, 0, then our constraint is going to be the equation of that circle. And that's going to give us x squared plus y squared is equal to 5 squared, or 25. So then we can use our constraint equation to eliminate one variable from our objective function. So I'm going to solve for y. You could just as easily solve for x, and you will get exactly the same thing. That gives us y squared is equal to 25 minus x squared. Taking our square root, we would get y is equal to the square root of 25 minus x squared. And we're only going to take the positive square root because we're only using the top half of the circle. We're not using the bottom half, which would be the negative square root, to do anything. So we substitute our y into our objective function, giving us q equals 1/2 x times the square root of 25 minus x squared. So now that we have our objective function, our goal then is to find its maximum or minimum values. So we need to take its derivative. So I'm going to rewrite it down here. 1/2 x times the square root of 25 minus x squared. To find our derivative, we're going to need to use our product rule. So our f is 1/2 x, and our g is the square root of 25 minus x squared. And that gives us f prime is 1/2. But then, to find the derivative of the square root of 25 minus x squared, we need to use the chain rule. So our g of u is the square root of u, and u equals 25 minus x squared. So then our g prime is going to be dg du times du dx. So dg du is going to be, we can write that as u to the 1/2 u to the negative 1/2 times du dx, which is going to be negative 2x. So cleaning that up a bit, our 2's reduce out. The u to the 1/2 goes into the denominator, so we get x, so negative x over the square root of u, but u is 25 minus x squared. So now finally, we're done with that chain rule. We can plug all of this back in to our product rule. So we have g f prime. So we're going to have the square root of 25 minus x squared times f prime, so times 1/2, plus fg prime, so that's 1/2 x times g prime, which we just calculated is negative x over the square root of 25 minus x squared. So now getting a common denominator, we have a 2 in both denominators, but we need to get the square root of 25 minus x squared, so we can make this a fraction over 1 and multiply both the top and the bottom by the square root of 25 minus x squared. So in our numerator there, we're going to get the square root of 25 minus x squared times the square root of 25 minus x squared, which is just 25 minus x squared. And then plus, here we're going to have x times negative x, so instead of plus, it's actually going to be negative, so we get negative x squared. And then all over our denominator, 2 times the square root of 25 minus x squared. So collecting up our like terms, we get 25 minus 2x squared all over 2 times the square root of 25 minus x squared. So now we need to find our critical numbers. So our critical numbers are going to occur when the derivative is equal to 0 or when the derivative is undefined. So if we set the numerator equal to 0, that's going to give us one critical number. Or if we set the denominator equal to 0. So we're going to have the 2 times the square root of 25 minus x squared is equal to 0. So we solve by adding 2x squared to both sides, giving us 25 is equal to 2x squared. Divide by 2, divide by 2. So we get x squared is equal to 25 over 2. Finally, we take our square root of both sides, giving us x is equal to plus or minus the square root of 25 is 5 over the square root of 2 is square root of 2. And if we want, we can rationalize our denominator by multiplying the top and the bottom by the square root of 2, giving us plus or minus 5 square roots of 2 over 2. And that's going to give us one of our critical numbers. The other one is when this is equal to 0. So we divide by 2, and we get the square root of 25 minus x squared equals 0. We square both sides, and that gives us 25 minus x squared is equal to 0. And that factors as the difference of squares into 5 minus x times 5 plus x equals 0. So we get x is equal to positive 5 or x is equal to negative 5. So those are our critical numbers. And if we go back to our original objective function now, we have q, it was equal to 1/2 x, and then we had times the square root of 25 minus x squared. If we check these two critical numbers over here, we're going to get the global minimum, which is 0. Because if I plug in 5, 5 squared is 25. 25 take away 25 gives us 0, so anything times 0 equals 0. So since we want the maxes, this isn't going to be helpful. These are going to be our minimum value, and they're going to have area 0. So those aren't the ones we want. Then our maximum is going to occur here at that value. And if we plug it in, we have q equals 1/2 times 5 square roots of 2 over 2 times the square root of 25 minus 5 square roots of 2 over 2 squared. So we simplify all of that up, and we get, well, 1 times 5 square roots of 2 is 5 square roots of 2. 2 times 2 is 4. Then inside our parentheses, 5 square roots of 2 over 2 squared is going to be 25 times the square root of 2 times the square root of 2 is 2 over 2 squared is 4. So then that gives us 25 minus 25 times 2 is 50 over 4. Getting our common denominator, 4 over 4. 4 times 25 is 100. So we get 5 square roots of 2 over 4 times 100 minus 50 all over 4. So 100 minus 50 is 50. So times square root of 50 over the square root of 4, and we can simplify those. So 50 is 25 times 2, so the square root of 50 is going to be 5 square roots of 2. So 5 square roots of 2 times 5 square roots of 2 is going to be 25 times 2, all over square root of 4 is 2, 4 times 2 is 8. So finally, we would get 25 over 4. So that's going to be our maximum area is going to be 25 over 4. All right. So now we are ready to move into our next section, which is 4.8. 4.8 is going to be a little bit different. We're going to be talking about Newton's method. So the idea of Newton's method is how do we find roots of arbitrary equations. So far, we've been solving equations that we could factor, or we had other methods. So Newton's method is an iterative method, which means we start off with an approximation, and the more times we iterate the method, the more accurate our approximation is going to become. So if we look at this picture we have right here, we're trying to find this 0 right here of our red curve. So the idea behind Newton's method is we guess some value close to what we're trying to find. So we would guess x1, and then we go up and we find the tangent line to the curve at x1. Then the tangent line to the curve, we could then set it equal to 0 and find its x-intercept, x2. And we hope, as we see in this picture, that x2 is closer to the solution we want than our original guess, x1. Then we move to the middle picture, we rinse and repeat that process. And so this is why it's called an iterative process. We then go down, find the tangent line to the curve at that point, once again, and then we find the 0 of that tangent line to get our next point, x3. So notice each time we do this, we get closer and closer to the actual solution to that equation. So here in our third picture, by the time we found our third tangent lines 0, x3 and x4 were getting, x4 especially, was getting very, very, very close to being exactly the same as the 0 we want. So this is one of the methods that computers and calculators do to find roots of equations. They just do this very, very quickly. But the idea of Newton's method is exactly this, with the equation of a tangent line and using its 0 to approximate the 0 of the function that we're trying to find. And the more we do it, the more times we iterate, the better our solution becomes. All right, so let's go ahead and derive that idea. So I'm going to draw a picture. And we're going to discover how we can do that. So in our picture, we had something like this. I'm going to just do a rough sketch. And we found the tangent line. So here was x1. And we have a tangent line. And we're trying to find this next point. So the ordered pair of this point is going to be x1 and f of x1, where f was our original function. Then we have this point right here. This was our goal. But this point, since it's on the x-axis, we know that its y-coordinate has to be 0 because it's an x-intercept. So y has to be 0. And we're looking for this point, x2, because that's our next approximation. So then, using all of this information, we have this point, and the slope of the tangent line here at this point M is going to be the value of the derivative, so f prime of x1. So we can use our point slope formula from college algebra, which is y minus y1 is equal to m times x minus x1. So we know our x1 and our y1 are going to be x1 and f of x1. So we're going to have f of x1 and this is going to be x1. We know our slope is going to be f prime. So this is going to be f prime of x1. And then we have our other point here, so we know our y value at this other point is 0. And we know that the x value, x2, is what we have right here. And remember, this is what we want. So we're going to solve that equation for x2. So to solve that equation for x2, we're going to distribute our f prime of x1 into our parentheses. So we get x2 times f prime of x1 minus x1 times f prime of x1. And then we're going to add x1 f prime of x1 to both sides of our equation. So then that would give us x2 times f prime of x1, so just writing this on the other side, is equal to x1 f prime of x1 minus f of x1. So then we divide both sides by f prime of x1, divide by f prime of x1, and we divide by f prime of x1. And finally, we get that our next approximation, x2, is equal to, these two guys reduce out, is equal to x1 minus f of x1 all over f prime of x1. So this gives us a formula for x2 based on this picture that we had up here, right? So starting at x1, we were able to solve for x2 by that formula, and x2 is x1 minus f of x1 divided by f prime, or the derivative of f evaluated at x1. Then we could do that process again. So to get x3, we would plug into this same formula, but x3 would be x2 minus f of x2 over f prime of x2, and so forth. So that would be our iterative process that would generate that entire sequence. So if we kept doing that, in general, we get the recursively defined sequence given by this. And so this is just the generalization that we were talking about of that formula. So to get the next sequence member, x sub n plus 1, it's equal to the sequence member that came before minus the function evaluated at the previous sequence member divided by the derivative evaluated at the previous sequence member. And as we saw in this picture, as we iterate this process, our solution will hopefully get closer and closer and closer to what we're trying to find. All right, so let's go ahead and use Newton's method to calculate the square root of 2 accurate to 6 decimal places. So before we do this, let's go back and look at Newton's method and see, well, what is it we need to know then? In order to use Newton's method, we're going to need an initial guess. So we need to guess x1, but we also need a curve that has the root or the solution that we're trying to look for. So in this case, we need a function who has an x-intercept or a 0 that is equal to the square root of 2. So one way we can do that is we're going to start with x equals the square root of 2, because that's what we want. And we're going to eliminate our radical by squaring both sides. And that gives us that x squared is equal to 2. And we minus 2 and we minus 2. So we get x squared minus 2 is equal to 0. So when we have an equation that is equal to 0, that has the x-intercept that we are trying to approximate, we can set it equal to f of x. So that is, our f of x then is the x squared minus 2. Because the 0 is the square root of 2. Because if I plug the square root of 2 in, the square root of 2 squared is 2, and 2 minus 2 is 0. So sometimes the hardest part of doing a problem like this is coming up with the f that has the right 0. Because now after we have f, the rest of this is just using this formula that we have right here. So to use our formula, we're going to need a guess, and we're also going to need to know the derivative. So the derivative of x squared minus 2 is equal to 2x. And then we need a guess. So we know the square root of 2 is bigger than 1, and we know that the square root of 2 is less than 2, because the square root of 2 is in between the square root of 1 is less than the square root of 2 is less than the square root of 4. But that tells us that 1 is less than the square root of 2, which is less than 2. So if we wanted to guess, there's a whole bunch of different choices. I'm just going to guess very simply that x1 equals 1. If you start with x1 equals 2, you're going to get the same answer in the end. We'll talk about, we do have to be a little bit careful about our guesses, but for this one it's not really going to matter which one we pick. So I'm going to guess x equals 1. And then our formula becomes x sub n is equal, or x sub n plus 1 is equal to x sub n minus f of x sub n. So that's going to be x sub n squared minus 2 divided by 2 times x sub n. So I just plug x sub n into my f that I had here. And I just plugged x sub n into my f prime, which I had here. So now we could do these manually by plugging some things in. So if I guessed x equals 1, so if I use n equals 1 to plug into my sequence here. So that means this n is going to be, oh, I've already used green, so let's not use green. Let's use blue. So this n and this n and this n and this n, that did not work out very well. Are going to be replaced with 1. And if I do that, that tells me 1 plus 1 is 2. So x sub 2 is x sub 1 minus x sub 1 squared minus 2 all over 2 times x sub 1. And our guess, x sub 1, is this. So we're going to get 1 minus 1 squared minus 2 all over 2 times 1. So if we simplify all of that out, 1 squared is 1, 1 minus 2 is negative 1. So we get 1 minus a negative 1 over 2, which gives us 3 halves. So that would be our first approximation of the square root of 2 would be 3 halves. Then we could do this process again and again and again and again. Well, turns out that that's a very, very long way to do this. So let's grab our calculator. So we have this formula that we calculated by plugging in f and f prime. So what we're going to do is put that into our calculator. And before we do that, though, we're going to take our guess. We guessed 1, so we're going to do 1 and just press enter. So then that puts the 1 into our calculator. So now our calculator believes that that's our answer. So if I press second and then the minus key down here, it pops up an answer on the screen. And if I press that, my calculator is going to give me whatever was entered on the previous line. So this is going to allow us to use this formula. So our next value, x sub n plus 1, is equal to x sub n. So basically, everywhere in this formula where we see an x sub n, we are going to replace it with answer. So we're going to go second answer minus, and then we grab our fraction, and then parenthesis, we have our answer, but we need to square it, minus 2, close our parentheses, over 2 times answer. And now when I press enter, notice my calculator gives me 3 halves, which is what we got when we did this manually. So now, to make our lives a little bit easier, if I want to do the same thing again, on my calculator I press second and enter, and it actually pulls up what I had on the previous line, and I press enter. So then it tells me that my next thing, if I iterate that process again, is going to be 17 over 12. So then x3 is 17 over 12. And now I can rinse and repeat. It turns out if you actually just press enter on your calculator, it will pull up what you did on the previous line again. So we press enter. So then what's my x4 is 577 over 408. And let's do one more. So we press enter on our calculator one more time. And finally, this time, we get this value. And our calculator finally ran out of memory to hold that as a rational number, so it converted it to a decimal for us. So then that is our x4 and x5 respectively. So x4 was 577 over 408. And finally, x5 was equal to 1.414213562. So just out of curiosity, what is the square root of 2? If we ask our calculator, we'll notice our calculator tells us exactly the same number after we'd used Newton's method 5 times. Our approximation of the square root of 2 was the same accuracy that the calculator has when calculating the square root of 2. So, interesting. So, to make sure that we all know how to do this on our calculator, it's now time for a U try. But before I turn you loose into groups, let's actually just get into groups. Alright, so to approximate the natural logarithm of 2 to 6 decimal places, what we're going to do is we start with x equals the natural logarithm of 2, and we're going to raise both sides to the e, and that will reduce out the e in the natural logarithm, so we get e to the x is equal to 2, and then we minus 2, and that gives us e to the x minus 2 is equal to 0. So then our f of x is equal to e to the x minus 2. And the derivative of e to the x minus 2, well, the derivative of e to the x is e to the x, and the derivative of negative 2 is 0. So we get our derivatives, and then we need our formula. So x to the n plus 1 is equal to x to the n minus f of xn, so e to the xn minus 2 all over e to the xn. And now we need a guess. So the natural logarithm of 2 is less than 1, so I'm just going to guess x equals 1. So that's going to be our answer. So I grab my calculator, and I put 1 in, and just press enter. And so now everywhere in my formula here where I see an xn, I am going to put answer. So I go second answer minus, grab my fraction, and then I'm going to have e to the answer minus 2 all over e to the answer. And I press enter, and that gives me my first approximation. So that's my x sub 2. There's x sub 3. And let's press enter 2 more times. And we'll notice something interesting. We don't need to do this for the problem, but if I press enter again, what do I notice about the last 2 entries on my calculator? Well, I noticed, did it change at all? So the answer is no. So then after 5 iterations of Newton's method, my calculator can't tell if it's getting any more accurate because it's actually ran out of memory. So that's my x2, this is my x3, this is my x4, and this is my x5. And x5 is definitely accurate to 6 decimal places. So in the actual question it says, find the natural logarithm of 2 accurate to 6 decimal places. Well, we know we're accurate to 6 decimal places when it doesn't change after 6 decimal places. So here we had 0.69404, 0.69314. So those were not the same. So x3 and x4 don't have enough accuracy. But now if I compare x4 and x5, the first digit's the same, second digit, third digit, fourth digit, fifth digits. Sixth digit is the same. So the first 6 digits of this are accurate, and we check. It was actually even more accurate than that, because if we compare these two, like I was mentioning, it's actually accurate to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 decimal places. And if we ask our graphing calculator, you notice it will tell us exactly the same number, that's what the natural logarithm of 2 is. So, all right. Hopefully we're all feeling pretty good about using our graphing device to help us do these. All right, so then our next example says find the local minimum of f of x equals e to the x minus 2x squared. All right, so we want to find the local minimum. To find local minimums and local maximums, we need to find critical numbers. So we need to find the critical numbers of f. The critical numbers of f are the zeros of the derivative. So the first thing we need to find is the derivative. So f prime of x is going to be equal to e to the x, and then the derivative of negative 2x squared is minus 4x. So then we want the zeros of this. So we're going to apply Newton's method to this. And just to make it a little bit clearer, instead of calling it f prime, I'm going to call it g prime. Because our formula then is going to be x to the n plus 1 is equal to x to the n minus g of xn all over g prime of xn. If we wrote that in terms of f, it would be x sub n, but since we want the zeros of the derivative, it would be minus f prime of xn divided by f double prime of xn. So the reason I wrote it as g was just to make clear that we're using the same formula. You don't have to do that, but the critical numbers are the zeros of the derivative, not the zeros of the original function itself. So then g prime is going to be e to the x take away 4, because the derivative of 4x gives us 4. So then our formula is going to be x sub n plus 1 is x sub n minus our g. So that's going to be e to the x sub n minus 4 x sub n, all divided by e to the x sub n minus 4. So now we need to guess a solution to this. So what would be a guess of a solution? Well, if we were to look at this, we want to know, well, when does the derivative equal to 0? So when would e to the x minus 4x equal to 0? Well, if we plug in 0, g of 0 would be e to the 0 is 1 minus 4 times 0 is 4 times 0 is 0, and 1 minus 0 gives us 1. So that's pretty close to a 0. So let's just guess x equals to 0. So we're going to guess x1 equals 0. And we're going to put that into our calculator. So we try 0. So then we're going to have answer minus alpha y equals. And then we're going to have e to the answer minus 4 times answer, all divided by e to the answer minus, oops, not in the exponent, minus 4, close my parentheses, and I hit enter, and it turns out I get 1/3. And I press again, I get 0.357, and I press enter again, 0.357, 0.357, and I get this for my solution. All right, well, let's go ahead and save that into my calculator. So if I store this in my calculator, I'm just going to store it as A. It gives me this value. So now, if I want to check that, I could put it back into G and make sure I'm getting what I think. So if I did E to the A minus 4 times A, what should I get when I press enter on my calculator? Well, hopefully I get the number 0. So indeed, we found a 0 of this. So we had 1/3 and then we had this, so it converged pretty quickly. So then I saved this in my calculator as A. Actually, I needed to press enter one more time, Oh, I just accidentally closed my calculator. Alright, so let me do that again really quick. So second answer minus So that's actually the one I want to store in my calculator. So I pressed it a couple of times. And then that one's the one that we store in the calculator. So now we checked that that does indeed give us 0. But now we got to go back, because what did the problem ask us to find? The local minimum, right? So we found a0, but we've got to be a little bit careful because we found a0 of the derivative, right? But let's draw a picture. So if I were to draw the original function, so let's graph it and take a look at it. If I graph e to the x minus 2x squared, if I zoom in a bit, so zoom in, when we look at our picture over here, what do we notice when we graph our original function? So based on what we saw, here we just found a critical number, and what was our critical number? 0.35. That's going to be this one, so that's actually going to be a local max. So if we look out here, there's another critical number, right? And it's going to be here. And we don't know what it is, but what should we use as a guess if we're trying to find that critical number? Well, we're going to need to guess something not 0. So we need to guess, say, x1 is equal to 2 to find the other critical number. So one of the things that Newton's method does is it finds the 0 closest to where we found. We guessed x equals 0, so it found where this graph had slope 0 here, but it didn't find this one because our initial guess was here. It only finds the one that is closest to what we are trying to find. So we rinse and repeat that same thing. Darn it, I closed my calculator again. So we're going to have to put in the same thing, but this time we're going to guess x equals 2. So we go 2, and we type that in. So second answer minus alpha y equals. When we press enter this time, enter, enter. All right, and there it finally stops changing. So the other critical number is x is approximately 2.153 ... And I'm going to put this in my calculator as b. So let's go ahead and store that in the calculator as b. Okay. So since we know that that's going to be our local minimum, we have to take that and put it back into the original function. So we get e to the b minus 2 times b squared. And that gives us our ordered pair for the local minimum of that graph. So the main point of this example was we have to be a little bit careful when we're using Newton's method. When we were asked to find the local minimum, I just blindly proceeded forward and found a critical number. But we have to be a little careful because a function can have more than one critical number, and Newton's method will only ever find them one at a time. So if that's the case, we have to make sure we're finding the right critical number by making sure our guess is close enough to the critical number in question. All right. So the reason that this must have at least one real zero, negative 2, 0, is from the intermediate value theorem. So we know that polynomials are continuous. And if we check, f of negative 2 would be negative 2 to the fifth minus 2 times negative 2 plus 3 gives us negative 32 plus 4 plus 3, which is negative 25. And f of 0 would be 0 to the fifth minus 2 times 0 plus 3, which would give us positive 3. So if we drew a quick sketch from negative 2 to 0, we would know at negative 2 we're down here at negative 25, and at 0 we're at like positive 3. So that means at some point between negative 2 and 0, our graph had to cross the x-axis. So then we would have f of x is x to the fifth minus 2x plus 3. And its derivative, f prime, would be 5x to the fourth minus 2. So then that would give us x sub n plus 1 is equal to x sub n minus x sub n to the fifth minus 2 x sub n plus 3 all over 5 x sub n to the fourth take away 2. So we need a guess. And I'm going to guess the midpoint of 0 and negative 2, which is negative 1. And then I would have my answer, take away alpha y equals, some parentheses, I'm going to have answer to the fifth minus 2 times my answer plus 3 over 5 answer to the fourth. Oh, the answer didn't take. So 5 answer to the fourth minus 2. And then I'm just going to press enter until it doesn't change anymore. So there we go, and it seems that then our approximation of that root is given by this value right here.